Hello. I always say hello at the beginning. The same way, hello. Like I'm surprised to see you, but hello. Uh, this is our second to last, our penultimate lecture for the semester. I'm sure you're very sad. Anyway, today, or I guess I should say down here, we're joined by our buddy, not Jules, Tybalt today. We have a fresh, fun and exciting cat here, little Tybalt. You might notice that he doesn't quite fill up the chair in the way that Jules does. Jules is very large. But yeah, this is Tybalt. Uh, he's a Baltimore native, just like me. Uh, and so he's gonna be hanging out with us today. Jules and I had a bit of a uh, I accidentally scared the poop out of him, I think. Um, he was walking around. I went to pick him up, and he wasn't like aware that I was gonna pick him up, and he freaked out, and he slashed my arm by like just in the mad scramble. So he's been scared of the office ever since, which makes me sad because he's my favorite part of my office. Anyway, all that aside, let's get into bloom filters. All right, here we are, bloom filters. So the first time I heard about bloom filters, I thought it was like a image thing, like it would add bloom effects to images or something. No. I I want to say it's not that fun, but I actually think it is that fun. It's just very differently fun. So, this is the last flower image we'll have here. So here we go. Um, so what is a bloom filter? Mm. Delicious Vasa. Um, so the purpose of a bloom filter is to sit in front of, to act as sort of a gatekeeper for a large, slow data store. You could think of it as a really large, um, it's raining to beat the band today, and I'm worried it's gonna like leak in my office because my gutters are busted. Anyway, I know you needed to know that detail of my life. Um, and so it sits in front of, it's a gatekeeper, so to speak, to like an internet resource or a large array of hard drives or a big data store that's pretty slow. And the question the Bloom filter answers is, does the resource that you're sitting in front of, so imagine like an old haggard figure sitting in the front of a large warehouse, and you go up to them and you say, "You there, Bloom filter? Yes. Do you have do you have Elmo's greatest hits on vinyl in there?" And the bloom filter goes, yes or no, right? So it just tells you whether or not you can go into the back and find the thing. Um, so another way of phrasing it, the more mathematical way of phrasing it, is to say that Bloom filters keep track of set membership. So Bloom filters are in charge of some set, one set. So we talked about multiple sets last time and how they get union together. Bloom filter's in charge of one really big set, like huge set. And the purpose of the bloom filter is to keep track of what things are in that set and what things are not in that set. And so you could give it anything in the world and it could look, the bloom filter should be able to look at it and say, is it in the set or is it not in the set? And no, Orlando Bloom, crying will not get you past this filter. You have to stay outside. Got to keep those blooms out. No, it's just named after its inventor, as many things are. So Bloom filters have two main operations, right? Whenever we talk about an abstract data type, um, or a data structure, or any of those things, we have to talk about what operations it performs, and it just has two: insert and query. Insert is just, I have a thing, I want to let the bloom filter know. Like imagine the bloom filter is some old haggard creature standing outside of a warehouse. When you go to add something to the warehouse, you go up to the creature and you say, "Hey, I'm putting this into the warehouse." It's a rubber ducky trying to masquerade as a rooster. I'm going to put that in the data warehouse. So you show it to the Bloom filter, and then you go put it in there. The Bloom filter itself does not store the ducky. The warehouse does. The databases or the internet API or whatever. The Bloom filter just needs to know that the ducky is in there. All right. So that's operation number one. The second operation is, I'm just going to grab items from my desk, is you go up to the Bloom filter and you ask it, do you have a fish, a folded fish in your warehouse? Is in that warehouse behind you back there? Is there a fish like this in there? And the Bloom filter will look at it and it will say yes or no. Now, there's no remove operation, you may have noticed. Actually, which is just like disjoint sets, we don't talk about remove, even though remove's not as big of a deal as it is for Bloom filters. There's no remove. Once something goes into the warehouse, it cannot be removed. You can't walk out of the Bloom filter warehouse and say, I'm taking this marker out, Bloom filter. You can now know that this isn't in there. Bloom filter would be like, does not compute. I don't know how to remove things. So, is this a reasonable constraint to put on a data structure? Well, since the rain's slowed down. Excellent. Since the data structure is standing in front of a very large internet or hard drive database of things, it's massive. Kind of assume people aren't going to go to the trouble of removing things from there. So all the Bloom filter has to know is what's gone in, right? It basically it performs its operation just with the prior knowledge of what it's seen going into the database. All right, here's another challenge. Again, this works better in person, but we'll try it online. So we have insert and query. We need a data structure that performs this filtering operation, or these two filtering operations, insert and query, in constant time, and you use at most 1 bit per piece of data in the overall collection. So if you have a data store if you have 1 million things in your warehouse, you must use at most 1 million bits. Actually, I'm gonna modify this. 2 bits. We'll say 2 bits. So we have a data store of 1 million entries, then that's 2 million bits, which is 41.66. All right, I hope I doubled that correctly. So last time I said don't use hashing because it's a dead end. This time I'm going to say use hashing. So we'll just stop here. I'll pause and we can have a discussion. A discussion. A discussion. A disgusting discussion. A discussion. Oh, all right. And we're back. And then, all right. What if I let you lie to me occasionally? What if your data structure can lie? How does that change what you're doing, or what would you lie to me about? So we'll do another pause real quick. Oh, and we're back. All right. So this whole notion of lying, or being wrong, allowing an algorithm or a data structure to be wrong some amount of the time, is what's referred to as a probabilistic algorithm or a probabilistic data structure. I love these. I really like these. I don't know why I like them so much. I just really like them. What's interesting about computing and solving problems with computing is that to solve a problem perfectly can sometimes be intractably hard. It's near impossible. But to solve it like 99% of the time correctly starts to get really much easier. And these are probabilistic data structures. They're not necessarily statistical data structures. It's different. When I heard probabilistic at first I was like, well, I mean, that sounds like How is that different from statistical? Kind of statistical, but really, there's not a whole lot of statistics in their implementation. The statistics and the statistical reasoning lies in proving how well they perform. That's when you have to do some statistical reckoning. The actual implementation doesn't involve much, if any, statistics, as opposed to machine learning when you're doing prior probabilities and applying Bayes' theorem and hiding your Markov chains and all those good things, all that good stuff. Those are statistics baked into the algorithm. These are probabilistic data structures are typically algorithms that are have no statistics in their implementation, but you have to use statistical reasoning to prove that they perform at a certain level. So, rather than say yes, so the old I don't know why I made it old. I guess because they're wise. You're old and wise. The person in the poncho outside of the warehouse that you ask, is this or that thing in there, right? Rather than forcing them to say yes, your data is absolutely in there, and or no, it's definitely not, you can allow them to lie to you sometimes. So um so instead your Bloom filter, instead of saying, yeah, it's definitely in the warehouse, your Bloom filter might say, yeah, I'm really pretty sure I saw that in the warehouse. I'm pretty sure I saw something like that go in there, right? And so with probabilistic data structures, you have to be careful about, well, like, what lies are we more or less comfortable being told by our data structure? So if we go up to the warehouse and we ask the person standing in front of the warehouse, hey, do you have uh, this can in there? And uh, if they said no, are we okay with them lying about that? If the can's actually in there? We're not very happy about that, right? Because we want the can and we weren't able to find the can. So it's not so we've basically been lied to, and therefore we can't get our data or our object or whatever. Okay. So what if we go up there and we say, "Hey, do you have this combination binder clip carabiner?" Look at I'm inventing. I'm on the cutting edge of innovation. This is multiple fasteners in one. Um and what if the data structure says, "Yeah, it's in there," and it's not? Are we okay with being lied to in that case? Well, I think we're a lot more okay being lied to, right? Because in that case, we're not going to walk away and say, oh, I guess it's not in there, because they said it's probably in there. So if we go in and I actually go and find it, yay, they were right. And if I don't find it, I'll be like, they were wrong. But at least I've not walked away from a situation where my data is actually available in there. So when we look at Bloom filters and whether or not when I call the find method, when am I okay for them to be lying to me? I'm not going to be okay with them saying, no, it's not there when it's actually in fact in there. But I can live with the fact that um they tell me it's in there and I go and look and it's not, right? In the case of like how bloom filters are actually implemented, what this looks like then is I ask the Bloom filter, do you have my data? And the Bloom filter says yes. And then I go to the slower data store that might take 15 milliseconds or something and find that it's not actually in there. But most of the time, that Bloom filter is going to be really useful because it's going to give me the correct answer. And hopefully, if we can keep the amount of times that the Bloom filter lies really low, then the amount of times that we're wasting our time will be very marginalized. Um, so it's also I also draw the analogy of like a clerk at a shoe store when you like go and you ask like, do you have this shoe in this size? And the clerk kind of acts as a bloom filter, right? In the sense that they might be, if they said no and they were wrong, you'd be mad. If they said, yeah, I think so, and they go back and they go, nah, it's not in there, you'd be mad, but at least they checked, right? At least somebody checked and so on and so forth, right? So Okay, so how do we actually implement this? So let's suppose we just hash the item we're being asked about. Um, and then that'll give us. So in this case, the Bloom filter will be an array of bits, individual zeros and ones. And so what we do is every time that somebody brings me an item, like this chip clip for this little bag clip, I would take this and I would come up with an integer value for it, and then I would mod that by the size of my bit array to get an index into that bit array. And then I'd go look in the bit array and I'd say, if there's a 0 there, I will say that there is no chip clip in my data store. If there's a 1 there, I will say, yes, there is a chip clip in our data store. Does that work? And what problems does that have? All right, chat? Chat, you're not actually here now, but chat? What's the problem with that? What did we learn about hashing that causes us headaches that we have to deal with? Right? It's collisions. So suppose that ChipClip and GoPro both hash to 783, right? And I actually put a GoPro into the data store. I said, "Oh, would you like this GoPro? Oh, here you go. Here you go." But I never put a chip clip in there. And so when I go and I ask, "Is a chip clip in there?" It'll go and it'll see that the bit for whatever I said, 783, it'll see that that bit's been flipped to 1, right? So there was a hash collision. And so now I'm going to falsely say, yeah, there's a chip clip in there, when in fact there is not a chip clip in there. So that means I can say chip clip's in there and be lying. Can I say chip clip's not in there and be lying? Right? So suppose this collision didn't happen. I didn't put the GoPro in there, and I go and I look in my Bloom filter for chip clip, and I see a 0. Will I ever be lying to someone if I say, yeah, chip clip 0? It's not there. No, I won't be, because nothing will have ever flipped that 0 to a 1. So I'm good, right? I will never lie about the fact that the thing is not in there. So collisions cause problems, but the only thing they do is they make it so that when we say, yeah, this thing's in the data store or in the warehouse or whatever, it means that we're going to be lying some of the time. And how do we quantify how often we'll be lying? We quantify that by our collision rate, right? The more collisions that our hash function has and our hash table, the underlying hash table have, the more times we're going to lie, which means we want a good hash function and we want to keep our loading factor low. So when I say that something is in the data store and it's not, that is called a false positive, right? When I say something's in the data store and it is, that's a true positive. If I say something's in the data store and or I say something's not in the data store and it is in the data store, that is a false negative. Bloom filters do not produce false negatives. They only produce false positives. So, whenever we say that something's not there, it is in fact not there. Which brings us to our would you rather. It doesn't bring us to our would you rather. That segue was a lie. All right. Welcome to this would you rather. Would you rather be immune to all diseases, pain, radiation, and can hold your breath up to 25 minutes, but have skin like a mole rat's and similar teeth? So basically, you are a humanoid version of this little mole rat. Look at this little mole rat. Look at it. Its teeth are outside its mouth. Um, or also all of these other things are true about mole rats. They Scientists have not found a disease. I believe they're also immune to poison as well. Um, Most pain, they're fine with radiation. They're basically they're little scrinkly superheroes. Or you can paint beautifully, but your paint strokes fade from existence, and any record of their existence. It's very Back to the Future-esque the way that your paint strokes fade within 2 hours. All right. So that's your would you rather. We'll freeze. Oh! All right. I hope that wasn't too short of a freeze. What if I gave you 3 bits? What if I gave you 3 bits per item in the data store? Well, that would reduce our loading factor, so that's nice. What else could we do? We could do more hashing, right? So before I was saying, I could give you. I love how I find all these weird things on my desk. Uh, Owlhead, right? And I could say I'm gonna hash Owlhead, and I'm gonna get 53, right? So I get 53 for Owlhead, and I go look at 53, and I say, okay, on a find, okay, at 53 I see a one, which means that I'm fairly certain that there is an Owlhead in my warehouse. Okay, what if I have two hash functions and I hash this little guy, right? It still comes up with 53 from the first one, but he also comes up with 72. So Owlhead hashes to 53 and 72. So what if 53 is 1, but 72 is a 0? Is there an owl in my warehouse? Is there? Chat? Chat's not here. I'm just looking at a picture of a kitten, actually. But chat, 50 is the owl in there? If 53 is 1 and 72 is 0, is the owl in there? No, because in our insert we would set both of them to 1. So if only one of them is 1, that means that the owl is in fact in there. And so what we've done to try to mitigate the problem with these collisions is to use multiple hashes. So by using multiple hashes, that means the owl would have had to have collided with two things in order to generate a false positive, right? So what we can do is we can increase the amount of storage, the amount of bits we have, which reduces our load factor, thereby lowering hash collisions. But then what we can also do is add more hash functions. So we can have two hash functions, three hash functions, four hash functions, meaning that we would have to have so many collisions for a false positive that now we're making false positives very, very unlikely. So let's look at another example where we have x is going to hash to this position, anywhere a blue arrow points. Oh, let me get my laser pointer. Uh, this position, and this position. For those of you who have color blindness situations, then y is going to hash to this position, and this position. And then z is going to hash to this position, and this position. Then if we ask, is w in the data store, we'll see that, yeah, it collided with y here, and yeah, it collided with x here, but it didn't collide with somebody here. So we can safely say w is not in the data structure. So the more hashing we have and the larger the array we have, the lower we can reduce this false positive rate. So what is the false positive rate? Uh, this is a bit of a whirlwind tour, so we're not going to get into the math of it. But the false positive rate for k number of hashes, n items in the array, and then m being the size of the array, uh, is 1 minus e to the negative kn over m to the k. Which, for those of you more mathematically inclined, you will realize that as m grows and k grows, this false positive rate goes down. It declines, right? So the larger the table and the more hashes we have, um, the better we perform. There's something else I wanted to say about this. Hold on, I'm gonna pause to think about it. Well, I couldn't think of it. I guess we're done. So that's it for bloom filters. Why do we go over bloom filters? Is it because they're super common? No, it's because they're super useful. They're pretty useful. They're used, I think, mostly in mobile development. You'll have bloom filters to determine what assets exist on the other side. Oh, I remember what I wanted to say. Hopefully, at this point, you understand why we don't have a remove function, right? If my friend Owl here has hashed to three different spots that might be colliding with other things, and remember, this is not a standard hash table. It doesn't have the key and the value there. It just has a bit 1 or 0. If I said I'm taking the owl out of the warehouse, then how would I know? I would know which bits to flip, but I might be colliding with other things, right? I might be flipping something to 0 for another item that is in the warehouse, which is why we can't have removes in a bloom filter because we don't have any way of if you gave me the array of bits and an item, I would have no way of recovering or knowing whether or not that particular item collided with other items in the data structure. So that's why we don't support a remove operation for bloom filters. If it's another this is the other point. The other thing is you also have to have some sense of how large your warehouse or whatever your large data store is going to be because you can't enlarge this array. It's stuck. Whatever size you put it at, you're stuck, right? If you wanted to enlarge the array, you would have to go inventory your entire data warehouse and rebuild the whole thing over again, which would be extremely costly. Um, so bloom filters, once you set the capacity, that's it. Once an item goes in, that's it, right? And so the nice thing about bloom filters is, like we said on several slides back here. Oh wait, I'm not on the slides. Go continue. Right, 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 right. If you have a data store of a million things and you want a loading factor of 0.5, then you could use 2 million bits, which is only 41 kilobytes, which isn't even a lot of data from back in the dial-up internet days. Um, so if you have a billion things, then you're looking at 1,000 times that, like 4 megabytes, which is still a pretty small index of a billion different unique items. And so most places don't have an inventory of a billion things. So 4 megabytes is going to let you store a very large amount of it let you in. This is effectively an indexing mechanism. Um, so yeah. All right. This is usually where I leave the room and give you guys time to fill out your student evaluations of educational quality. I may have already mentioned this in a previous lecture, but if I haven't, this is in the slides where I do that. Um, you could fill out these forms and give numeric feedback on how well a course worked for you, and then you can also write out suggestions for what worked in the course, what didn't work in the course. The SEQ, the numeric feedback, is used for performance evaluations of faculty and things like that. And it's sort of public. It is published information. You can find the SEQs for everybody on the UMBC website, which I recommend you do instead of using things like Rate My Professor, because Rate My Professor reviews tend to be people who really loved a class or really hated a class, and so you don't. SEQs actually tend to capture everybody's opinion, not just the people who were uh, love or hate about a particular class. So you get a little bit more fine-grained feedback in those numbers. It's an average of a lot more feedback. Um, the direct instructor feedback forms, the diffs, where you write stuff out, that just goes to me, and I can't access them until grades are submitted. I don't see them. I typically wait a little while, even past that, to look at them. But that's where you can give feedback on the class. And it's going to your professors. Feedback for this class is going to me. It doesn't go to anybody else. So if you air your grievances, the only person who's going to see them is the instructor. Which I encourage you, when you leave feedback in these forms, really try to make it constructive feedback, right? If you're taking the time out of your day to do this, great. And so this gives you an opportunity to help the instructor improve the class for later semesters. Or if you expect to take that instructor again, improve their class for maybe you take a different class with them. And so I encourage you to fill out these forms, but also when you're giving feedback, don't just say lectures were boring or uh, I didn't, the exams were unfair or something like that. Um, Try to come up with ideas. Well, what would make the exams more fair? What would make the lectures more boring? What would make it easier to focus, or any of these other things? Don't just provide positive or negative feedback. Provide substantive structured feedback, especially for positive feedback, saying that the class was great is great, but if you can think of two or three things that really made the class sparkle, made the class shine, or three things that really could improve the class, um, go ahead and put them in there. And so we instructors can look at that information and actually take action items. Can't tell you how many times I've read like slides were bad. I'm like, why? Why were my slides bad? I mean, they're not my favorite part of my class either, but why were they bad? So I encourage you guys to fill that stuff out. Um, and yeah, and I learned a lot from them, especially when I was a more novice instructor. Sometimes it's funny though, you'll get conflicting feedback. Somebody will be like, "I love all the gifs. The gifs that I put in my slides are mega points of contention. A lot of students love them and they say they're great memory aids, and then some students say that they're distracting." So I left them in because they're fun. Like I broke the tie with they're fun and they're already there. But I actually did add more because it seemed like there was a bit more feedback from students that gifts were interesting and good memory aids. So I left them in. So a lot of stuff that's done in classes might just be because it benefits the most people. So if you can get your feedback in there, you can help tilt the needle one way or another. Anyway, that's all I'll say about that. One more class after this. I'm excited. We're going to do amortized analysis. It's probably not the last time you're going to see it. I hope it's not the last time you're going to see it. And then we're done with lectures for the semester. All right. See you guys later.